Alrighty, hello, and welcome to our final class of week 5. Alright, so let's see. Okay, right. Today we're going to be finishing up chapter 7, hopefully, probably, possibly cracking into chapter 8. Neither of which are on the second exam, which will open tonight, or not tonight, at 12 a.m. tomorrow morning. Right, it opens at midnight, closes a minute before midnight on Sunday. Before that happens, of course, we have a glorious 3 hours of office hours. So we'll have plenty of time to get into all of your questions, last minute questions before the test, and then I will go radio dark until Monday. Alrighty, so let's go ahead and dive in. So we are talking about intermolecular forces, right? The forces that draw molecules together, that attract molecules to each other. Hang on one second, we're getting a little background interference. So I need you to relocate it, because it's all the talking is coming through the mic. Alright, I am back. I'm sorry. My kids know not to be one room over and shouting, but it seems, even though they know it, got to remind them on the regs. So thank you for being patient. Okay, so we're talking about intermolecular forces, and we started this conversation yesterday by talking about London dispersion forces. I just wrote a nonsense word. I apologize. Hang on. Alright. Getting our head in the game. London. There we go, dispersion. We were talking about London dispersion forces yesterday, and that this attraction is based on a temporary charge separation in the electron cloud of atoms and molecules, right, inside their orbitals. Now, one thing to be aware of is, and that this is the last thing I want to say about London dispersion forces. Let me turn off silence my cell phone. The last thing I want to talk about London dispersion forces is the strength of the force. The strength of the attraction gets stronger the larger molecules get. So, for example, if you were to compare the London dispersion forces between F2 and Br2, alright, and if we open up our periodic table to compare these two atoms or two molecules together, if I were to ask you which has a stronger London dispersion attraction, fluorine or bromine, the answer lies with their position on the periodic table. So fluorine is right here on the second period, right? I'm going to do that in blue. 1, 2, 3, 4, 5, 6, and 7. Fluorine's on the second period, whereas bromine is on the first period, all right? And the larger your orbitals are, the stronger the London dispersion attraction will be, between two molecules. And so, for example, fluorine, right, we've got two fluorines bonded together. Their orbitals are on the second period, right? Whereas bromine, even though, sorry, I forgot to draw all of my lone pairs in my Lewis structure. Bromine, even though the Lewis structure looks very similar, and here I'm not forgetting all of my lone pairs this time around, because we're on a lower period, it means our orbital size is much bigger around bromine. And when we talk about London dispersion, larger orbitals result in stronger attraction, stronger London dispersion attraction. So if you were to be asked, of these two molecules, F2 or Br2, which one has stronger London dispersion forces, stronger London dispersion attraction, you'd roll with bromine because the atoms are bigger. Alright. Okay. Next time, just okay, babe? Okay. All right. Okay, so I apologize for that again. They know they're not supposed to come in during class. Okay. So off to a rockier start, but that is the last thing I want to say about London dispersion forces. Let's move on to dipole-dipole attraction. All right. Now, you'll recall from yesterday we have three forces we're talking about, three different types of attraction: London dispersion, dipole-dipole, and then hydrogen bonding. We've covered the first and the weakest, London dispersion. Now it's time to move to the middle child, which we call dipole-dipole. All right, dipole-dipole forces. Now, the cool thing here is we've actually already done all the heavy lifting we actually already know what dipoles are. We've done all the heavy lifting about coming to terms with these, coming to grips with what dipoles are and understanding them. We just haven't called them as such. So turns out, polar molecules, and we know how to determine whether or not a molecule is polar, right? Polar molecules experience dipole-dipole attraction. All right, with London dispersion, we said that everything experiences London dispersion forces, right? Absolutely everything. Dipole-dipole attraction is a type of attraction specific to polar molecules. So if you have two polar molecules, they'll experience dipole-dipole attraction to each other. And it is based on, dipole-dipole attraction is the attraction between a permanent charge separation within the molecule. All right? It is the attraction between a permanent charge separation between the molecule. What are exactly we talking about? Yes, Carenza, that is correct. The larger a molecule is, the larger an atom is, the stronger the London dispersion attraction. Now with dipole-dipole, the type of attraction we're talking about is like this. So if you consider a molecule of HF, hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. So the difference here in electronegativity is 1.9, which means that this bond and molecule is polar. All right, HF is a polar molecule. That means that the electrons spend more time around fluorine, than they do around hydrogen, and so fluorine will develop a partial negative charge, and hydrogen will develop a partial positive charge, and those partial charges are permanent. That means when another molecule rolls in, it's not going to roll in like this. Right? A second molecule of HF could either roll up like this, or it could roll up like this. All right, and we know partial minus on fluorine, partial positive on hydrogen. The molecule of hydrofluoric acid that I've drawn up top is not, a second molecule of HF will never roll in like I've drawn this one, because negatives repel negatives, right? And positives repel positives. Right? Negatives repel negatives, positives repel positives. However, the one on the bottom is lined up so that the partial positive on one end of the molecule is lined up with the partial negative of the other, and the partial negative on one molecule is lined up with the partial positive of the other. This attraction, this is dipole-dipole attraction right here. It's the attraction between the positive end of one molecule with the negative end of the other, and vice versa. So when we talk about dipole-dipole attraction, only for polar molecules, and it's the attraction between the partial positives and negatives. That's what draws them together. Cool? So that is dipole-dipole attraction. Now let's take a look at hydrogen bonding. All right, hydrogen bonding. Hydrogen bonding is the strongest of these three intermolecular forces, and in order for a molecule to be able to hydrogen bond, you need two things. First, you need a hydrogen bonded. You need a hydrogen, I'm going to say attached to either nitrogen, oxygen, or fluorine. All right, it's not just enough to have a hydrogen somewhere in the molecule. It must be attached to nitrogen, oxygen, or fluorine. And then the second thing you need is you need to have a lone pair a lone pair somewhere in your molecule. Your molecule has to have hydrogen attached to nitrogen, oxygen, or fluorine, and it has to have a lone pair somewhere in the molecule. All right? If these two criteria are met, then you have a molecule that can engage in hydrogen bonding. All right? Now, Now that we know the criteria for hydrogen bonding, let's look at what it actually is. Okay, what is this? This force? Well, let's look at a water molecule. All right, we know, for example, that water has polar bonds because oxygen has an electronegativity of 3.5, hydrogen is 2.1, so our difference here in electronegativity is 1.4, making these bonds very polar. All right, so we have polar bonds in this molecule, and we know what that means for our structure. All right, because we're polar, we know that we have a partial negative charge on our oxygen, and we have partial positives on our hydrogens. All right, partial negative, partial positives. Now, we know what will happen when another water molecule comes rolling in. We know that the oxygen on the second water molecule will be attracted to the hydrogens on the first one because the oxygen bears a partial negative charge and the hydrogens bear partial positives. All right, so there's going to be an attraction between the positive and negative dipoles. However, something that's just dipole-dipole attraction, which water has, dipole-dipole attraction, but something more is going on, something bigger. All right, something special happens when you have a hydrogen attached to nitrogen, oxygen, or fluorine, and a lone pair somewhere on your molecule. So we have that hydrogen here, and we have our lone pair right here. Okay, hang on. Sorry, it looks like my video feed froze. Okay. Give me 1 second. Whoops, sorry, this camera is scary. There we go. We'll just roll this smaller me, or bigger me. There we go. Okay. That's a terrifying angle. And let's just remove this. Okay. Okay, back to normal-ish. Apologize for the technical difficulty. So we should be good. Okay, so we have a lone pair on our oxygen, and we have a hydrogen that's directly attached to oxygen on the other molecule. Now, what happens is this lone pair is made of 2 electrons, and as we know, electrons are negatively charged, attracted to positive charges. So they are very, very, very attracted to this partial positive on hydrogen, and what they start doing is they start reaching out in an attempt to form a bond with that partially positively charged hydrogen. All right? They're trying to form a bond to that hydrogen. Here's the problem. This hydrogen is already in a committed relationship with another oxygen, right? It's bonded to that oxygen. It doesn't want to leave that other oxygen, but it also likes the attention it's getting from this new oxygen's electrons, all right? So it kind of accepts this second oxygen's attention. It will let it kind of do boyfriend things for it, but it's not going to actually break up with its original oxygen. It's not going to leave that committed relationship And so basically, hydrogen bonding is one hydrogen teasing the lone pairs on another oxygen. And that attraction keeps that second oxygen there, hoping it can make a new bond. And the hydrogen keeps it always in suspense. And that is hydrogen bonding in a nutshell. So that's hydrogen bonding. Let's get a little bit of vocabulary. Vocabulary in there. These lines right here. This is the hydrogen bond. All right, so if you're doing homework and they say draw the hydrogen bond, that's what they want you to show, those lines in between the electrons and the partially positive hydrogen. Yeah, totally. Now, the molecule that provides the hydrogen in the hydrogen bond, yeah. Because, you see, the thing is, because we've all been there, right? We've either been the hydrogen in a hydrogen bond or we've been the lone pair. But either way, it's relatable. If you're providing the hydrogen, if you're the molecule that brings the hydrogen to the hydrogen bond, you are called the hydrogen bond donor. And if you are the molecule that provides the lone pairs, you're called the hydrogen bond acceptor. And I believe there are homework problems at the end of this chapter that may ask you to draw a hydrogen bond or label the hydrogen bond donor, hydrogen bond acceptor. And so with this information, you can now take that and do it. All right, so for example, you could get dished up a problem like this. Draw the hydrogen bonds between two molecules of NH3 and label the H bond donor and acceptor. All right. So here is a so here's how you do it. So first, we got to draw the Lewis structure for NH3, and you'll notice that NH3 ammonia meets both of the criteria that we need to engage in hydrogen bonding. It has a lone pair, and it has a hydrogen directly bonded to nitrogen, right? It's bonded to nitrogen, oxygen, or fluorine are the three atoms you got to watch out for. All right. Now, to draw the hydrogen bond itself, you just draw some hatched lines in between the lone pair on one molecule and the hydrogen on another. So that is the hydrogen bond. The molecule that is providing the H in the hydrogen bond is the donor, and the molecule providing the lone pair in the hydrogen bond is the acceptor. All right, so that is hydrogen bonding. So at this point in time, we have covered all of our intermolecular forces, London dispersion, dipole-dipole, and hydrogen bonding. Now the question really is, what can we do with these intermolecular forces? All right. Now that we understand where they come from, know how to analyze a molecule to determine whether or not which ones are present, what are they good for? And they are good for the following. So intermolecular forces have a direct influence, correlation on bulk properties of your compounds, properties such as boiling points, melting points, and vapor pressure. All right? And it turns out that the strength of the intermolecular forces determines the properties like boiling point, melting point, and vapor pressure. And stronger intermolecular forces result in higher boiling points, which I'm going to abbreviate as BP, melting points, melting, which is MP, and vapor pressure. Well, higher boiling points and melting points, gotta qualify this, and lower vapor pressure. Which is VP. Okay. So with this in mind, this is how you're going to be encountering, and again, not on exam 2, but the third exam, you'll run into this. Exam 2, you'll run into stuff like determine whether this is polar or non-polar, or this molecule. But on exam 3, you're going to run into problems that ask you to, so this will be the question. You will totally run into questions like the following. Rank each molecule from highest melting point to lowest. And then I'll give you a string of molecules and you'll have to figure out which one has the highest boiling point, which is the lowest boiling point, all based on this. The stronger intermolecular forces result in higher boiling points, and melting points, or I could flip it and ask you about vapor pressure, lower vapor pressures for stronger intermolecular forces. Okay, so that's the question type. Let's get a couple examples under our belt. All right, so so it's rank from high to low melting point. And let me give you some molecules. Let's see. Susan, great question. And the answer is there we go. The answer is guaranteed. There will be different types of intermolecular forces in problems like these. So we'll go here. We'll go. hydronium. We'll do carbon tetrachloride. Which always takes a long time to draw because you have to draw 24 lone pairs. Yes, that is 48 dots to draw that dude correct. Let's see, let's do one more. How about we do, here's a good candidate. We'll do carbon trihydride monochloride. I'm going to space these out a little bit better. All right, so the first question is if we're going to rank these from low melting point to high, or high to low melting point, we need to know what intermolecular forces each molecule experiences, because the strength of the intermolecular forces determines how high the melting point is, right? The stronger the forces are, the higher they'll be. So we need to figure out which intermolecular forces are experienced by each molecule. And here's the thing to remember. Every single molecule will experience London dispersion forces. All right? Every single molecule that you run into experiences London dispersion forces. So you can automatically write LD under each one, right? Automatically. If you're shown a molecule and asked, does this have experience London dispersion attraction? The answer will always be yes. All right? They all have access to that weakest form of attraction. Now now we have to take each molecule kind of sequentially, looking at our first one. In order to determine whether or not you have dipole-dipole, you need to know, are you polar? And if you look at carbon's electronegativity is 2.5, hydrogen's is 2.1. This makes our electronegativity difference 0.4, so this molecule is non-polar. All right, it's non-polar, so if the bonds are non-polar, the molecule can't be polar either, so we don't have dipole-dipole in this molecule, and we also don't have hydrogen bonding, all right? There's no hydrogen bonding because for hydrogen bonding you need two things, a lone pair and a hydrogen that's attached to oxygen, nitrogen, or fluorine. Carbon's not on that list. Plus, there's no lone pair, so no dipole-dipole, no hydrogen bonding for our first candidate. All right, now moving to our second candidate. First, we need to know, is this polar? Oxygen has an electronegativity of 3.5, hydrogen 2.1. So our difference here in electronegativity is 1.4. This is polar bonds. All right, polar bonds. Does it mean that it's polar? And here, yes. You can see that you have 1, 2, 3, 4 groups around our central atom, but they're not all the same. If they were all the same, it's non-polar, but since they're not all the same, we have a polar molecule. So hydronium, which is the polyatomic ion we're dealing with here, has dipole-dipole forces. Now, does it have hydrogen bonding? All right. For hydrogen bonding, you need two things. You need lone pair, at least one lone pair, and it does, and you need an H on nitrogen, oxygen, or fluorine. It has both of these, so it does have hydrogen bonding. Hydronium has all three intermolecular forces. All right. Moving on to our second one. And this one, I feel like I've been botching the electronegativity for chlorine lately. So I'm just going to check it, double check it. The bond polarity. Okay. So the difference in electronegativity between carbon and chlorine. Chlorine is 3.0, carbon is 2.5. This means our electronegativity difference is 0.5, which is, these are polar bonds. We do have polar bonds, but you'll notice we have 1, 2, 3, 4 groups around our central atom, and because it's the same at every position, that means our molecule will be non-polar. All right, so carbon tetrachloride does not experience dipole-dipole attraction, because even though it has polar bonds, those all cancel each other out due to symmetry. You have the same thing at every position around your central atom. Now, looking at our final molecule, we know, I'm gonna just make a little barrier here, that, because we've already calculated these before, the electronegativity difference between hydrogen and carbon is 0.4, which is nonpolar, but the electronegativity difference between chlorine and carbon is polar. Right, so right here, we have polar bonds. And you'll notice that this molecule isn't symmetric. You've got 4 groups around your central atom, and they're not all the same. So this molecule will be polar, will have dipole-dipole forces, because it has a polar bond and it's not canceled out by symmetry around the molecule. The question is, will it also have hydrogen bonding? All right. Now, to do hydrogen bonding, you need a lone pair, which we have, right? We've got lone pairs on that chlorine. But you also need a hydrogen on oxygen, nitrogen, or fluorine, and it does not have that. It has only as hydrogens on carbon, so we do not have hydrogen bonding in our last molecule. All right? So at this moment in time, we have determined the intermolecular forces for each molecule we're assessing. Now we got to rank them. All right, we got to rank them, and I'm going to call the first one A, B, C, and D. All right, A, B, C, and D. And I'm going to clear a patch here. Just because I'm out of space, but I also don't want to redraw everything. So give me 1 second. All right. So we have A, B, C, and D. And we want to rank each of these from our high point to our low point. Question, is it possible for a molecule to have hydrogen bonding back? Oh! Kate, great question. Excellent question. It is not possible. The molecule is capable of hydrogen bonding then it automatically has dipole attraction as well. Excellent observation. If a molecule can hydrogen bond, it will automatically have dipole-dipole forces as well. All right, so ranking these from high to low, on the high end of things, we have a clear winner, and that is B, because hydronium, molecule B, is the only one that that has hydrogen bonding, right? We know the strongest intermolecular forces result in the highest melting point. So B has the highest melting point of these candidates. Now, ranking our second, also fairly straightforward, because of our three candidates left, our A and C only have London dispersion, whereas D has London dispersion and dipole-dipole. Again, dipole-dipole is a stronger attractive force than London dispersion, so that gets our second spot. The question really comes with comparing molecule A to molecule C, because they both only have dipole-dipole forces, and so the question is, how do you break that tie? The answer comes with size. Hydrogen is small. It's on the first period. Chlorine is bigger. It's on the third period, and we know that London dispersion attraction is stronger for larger molecules, all right? So the carbon's a tie, but 4 hydrogens versus 4 chlorines are all much bigger. They're going to have stronger London dispersion forces, and so we would expect them to have a higher melting point. So you go B, D, C, and then A is how we would rank these 4 molecules high to low. Cool? All right. There's plenty more practice problems like this at the end of the chapter. Susan, great question. So Susan's question is, what if you've got stuff that are all in the same period, and I am here to tell you that I promise to never give you a pure tie. There will always be a tiebreaker in the choices that I give you. So you don't need to worry about, like, what if I gave you, a molecule where all the molecules are second period and another one, and they only have London dispersion. How do you know? I won't give you that sort of situation, because there really isn't any way to know. Like, if you gave me those 2 molecules, I wouldn't be able to figure it out. And if I couldn't, there's no way I could possibly ask you. So you don't have to be afraid of that sort of tie. If you have 2 molecules, both with London dispersion, find the one with larger atoms, roll with that. Or what if you have 2 molecules with both have dipole-dipole? Again, look for the one with stronger London dispersion, roll that way. Okay, all right, that is the official end to chapter 7, if you can believe it. So it's over at long last. Pushed us a little back in the tentative lecture schedule, but not too awfully bad. All right, now, kind of in review, Chapter 7 was more or less about phases of matter, right? It was about, looking at the gas phase, liquid phase, solid phase. We spent most of our time on the gas phase, but then the end got back around to the others, talked about melting, changes in matter, melting, freezing, sublimation, deposition, boiling, and condensation, right? All those great things. 3 phases of matter. But you may be wondering, like, well, wait a minute. I've seen in this class more than 3 phases of matter. There isn't just solid, liquid, and gas. What about that thing that pops up? What about the aqueous phase? And I'm so glad you asked. It makes my transition easier. Because here's the deal. The aqueous phase is not a phase that pure matter can take. All right? Because the aqueous phase is a substance is in the aqueous phase when it's dissolved in water. This means dissolved in water. All right? It means dissolved in water, and so by definition, the aqueous phase is a mixture of 2 things. So pure matter cannot exist in the aqueous phase because the aqueous phase is water plus something else. It's a mixture, all right? And it makes a special type of mixture called a solution. So this is a mixture called a solution, kind of like a streetcar named Desire. And solutions are so important to chemistry that they get their own chapter, and that chapter is Chapter 8, which is where we are now. Just so you don't get confused by my shorthand, I will be writing the word solution a lot. So to avoid writing the full thing, if you see me write, or I will be writing solution as like this. Solution. That's kind of the shorthand I'm using. If you're wondering why, it's because that's what my calculus instructor would do when I was in college. Anything that ended in a shun, he'd just write an N with a little line under it. I don't know why, but he did it, and he was an awesome teacher. So I guess this is like, what you do when you're a kid and you put on your dad's shoes. It may not fit. I hope they don't fit you. I'm thinking about like my 2-year-old wearing my shoes. Hopefully your 2-year-old can't fit your own shoes. But you try to step into your parents' clothes, right, to be like them, and I guess that's where I get that. Not I guess, I know that's where I get that. But anyways, don't be confused. Now you know I'll write solution like this for the rest of the time. So what is a solution more specifically? We all kind of have an intuition of what a solution is, right? But let's get down into it. A solution is it equals something. So you're like, yep, I knew that already. Solution is something. A solution is something dissolved in something else. All right, that is what a solution is. It's something dissolved in something else. And This something, the something that gets dissolved, is called the solute, and the something else it is dissolved in is called the solvent. Alright, so usually we think of the solute as the solid and the solvent as a liquid, the one thing that we dissolve in the other thing. But actually, solutions are not, they're not restricted to solids and liquids. They're all types of solutions. So, for example, you may not be aware of this, but yeah, some things. Yes, exactly. You can have a solvent. You can have a solvent that is a gas. All right, a solvent can actually be a gas or a liquid. It's possible for a solvent to be a liquid, possible for a solvent to be a gas. Now, the types of solutes that are able to that can dissolve in a given solvent is determined by the solvent. So, if you have a gas solvent, you can only dissolve other gaseous solutes. All right. Now that might be weird to you, but an example of a solution that has a gaseous solvent dissolving other gaseous solutes would be the atmosphere. Thank goodness for this gaseous solution, right? The atmosphere is 78% nitrogen. All right, it is almost exclusively, not almost exclusively. I should say it is predominantly nitrogen gas. All right, and the other gases present in our atmosphere, like water, like oxygen, like carbon dioxide, like ozone, like argon, those are all solutes, gaseous solutes in the solvent of nitrogen, of N2 atmosphere. So the atmosphere is an example of a gas solvent, N2, dissolving other gaseous solutes like O2, like H2O, etc. Now, liquids can have more than, there's a bunch of different types of solutes that liquids can have. Liquids can have gaseous solutes. So you could have a liquid solvent and a gaseous solute. You could have a liquid solvent and a liquid solute. And you could have a liquid solvent and a solid solute. All right? And actually, you've experienced and actually probably consumed examples of each one of these. One example of a gaseous solute in a liquid solvent would be the carbon dioxide bubbles in soda or your carbonated beverage of choice, right? Those bubbles, when you crack open a can, product placement, and you hear that and the bubbles start coming out, those bubbles are carbon dioxide gas, which is a solute that has been dissolved in water. All right. It's also another great example of a gaseous solute would be oxygen in water. So when a fish is like swimming in a lake, I used to think when I was a kid that a fish's gills, because fish's gills let fish breathe. I used to think that the gills stole the oxygen atom out of water molecules, and that's how fishes breathe. But it's not. It's not. Fish's gills do not alter the molecular structure of water. What they do is the gills filter out oxygen gas that has been dissolved in that liquid water. It filters out that gaseous solute, so the fish is actually breathing the same O2 molecules that we are. It doesn't get them from water. It gets the O2 molecules that have been dissolved in water. This is also why when a pond, I don't know if you've ever seen a pond that's like mostly evaporated at a really low level. The fish, if the population of fish is too great for a body of water, they all start dying. They die because they're suffocating, because the fish are filtering out the oxygen gas molecules, solute, from the water before it has enough time to get replenished by the atmosphere. So that's another example. Brianna, sugar. Yes, absolutely. So sugar would be a solute in water, just like your morning cup of coffee. Your morning cup of coffee is a great example of a solid solute inside a liquid solvent, right? You put that solid sugar into your thing, stir it up. That's the solute in the solution of coffee, or which actually, coffee is actually an interesting example because it's got multiple solutes. The reason why it's brown is because it's dissolved the roasted coffee beans. So you've got roasted coffee beans, you've got sugar, and actually, if you add cream, there's also a liquid solute in that mixture as well. Yeah, totally. If you're wondering what a liquid solute would look like in a liquid solvent, I just said cream and coffee. There's one example. Also, another example would be the ethanol in vodka. Ethanol is a liquid, and vodka, actually all alcohol really, is just a solution of that liquid solute inside a water solvent. And actually, I don't know if any of you are familiar with the alcohol Everclear. I hope you're not, because it's disgusting. There are definitely better ways to better things to be drinking. But Everclear is 90% ethanol. Most of our alcohols are ethanol dissolved in water, but Everclear is 90% ethanol and 10% water. So in Everclear, it's actually a water solute inside a liquid ethanol solvent, whereas most other alcohols are an ethanol solute inside a much larger water solvent. So the weird thing with liquids is it depends upon which one's in the majority that determines solute versus solvent. Whereas gases in a liquid, solids in a liquid, the roles of solute and solvent are more clear, more defined. All right, so let's see where we are. All right, so it turns out that not every solute dissolves in every solvent. All right. Some of it is controlled by intermolecular forces, not all of it is. But there are factors that can alter the amount of solute that any specific solvent can dissolve, all right? And when we talk about the amount of solute that can be dissolved in a solvent, we're talking about a phenomenon called solubility. All right, solubility. So, what solubility is it simply the amount of solute that can dissolve in a given amount of solvent. All right, it's the amount of solute that can dissolve in a given amount of solvent. For example, sodium chloride, right, table salt, is very soluble. Whoa. Oh man. Hey, Susan, you are not too far off. Sorry, I have to get the perfect response. And... oh, will it not? Lame. Sorry, I had an amazing GIF of Yoda sensing things in the Force, but it won't let me paste it into the chat. So that's lame, YouTube. Let's get GIF support in your chat service. Anyways, and here I've just been sitting trying to paste a Yoda GIF with sodium chloride is very is very soluble in water. All right, sodium chloride is very soluble in water. If you're wondering how soluble, it turns out that 1 gram of water can dissolve 0.36 grams of sodium chloride. Now get this. That means that water can dissolve 1/3 of its mass in salt. That's kind of crazy. You like have a sample of water, it can dissolve, it can absorb 1/3 of its total mass in sodium chloride. The thought that counts it is. Well played. Alright, sodium chloride is very soluble in water. An example of a very soluble salt. In contrast, silver chloride is sorry, gonna start this a different way. So little of silver chloride can dissolve in water that it's considered not soluble or insoluble. Alright, so little of silver chloride can dissolve in water that people just say it doesn't dissolve at all. It's not technically not one. It's not exactly true, but get this: 1 gram of water can dissolve. Where was that? 0.00002 grams of silver chloride. All right, 1 gram of water can dissolve next to nothing. Look, I mean, 0.00002 grams of silver chloride. Our mass scales that we have in our teaching labs can't even measure that far out. So it's considered to be insoluble because so little of it goes into water. All right, so different compounds have different solubilities. There are a bunch of different effects and parameters and things that we can manipulate to change the solubility of a compound. For example, temperature. For example, temperature affects solubility. Pressure can affect the solubility of a gas. All sorts of things can influence the solubility, either increasing it, decreasing it. But we have 3 minutes left of lecture, or 2 minutes. And so I'm going to save those topics for lecture on Monday. So we will pick up Monday with chapter 8. So we'll pause here. And so anyways, we'll put a pin in lecture here, take a break, come back in 30 minutes, and then hit office hours to launch everyone into exam taking town. Cool. All right, thanks everybody for showing up, for tuning in, and I will catch you in 30 minutes. Later.